Hi, this is Pat Caplow. I'm solving problem number 22 on page 66 of Chapter 3 in the Giancoli textbook. The problem reads, a football is kicked at ground level with a speed of 18 meters per second at an angle of 35 degrees to the horizontal. How much later does it hit the ground? This problem can be made a lot easier by understanding some of the symmetry involved in projectile motion. So in this problem, I'm going to make a quick sketch. I've got my football, and I'm going to say that I'm going to go ahead and draw the ground level in here. And I can draw the path, the trajectory that the football will make. We know from class that it's parabolic, and that we could solve, as we have in class, for the time t that it takes for the ball to reach from its initial position to where it lands. We should also recognize there's some neat symmetry here of the idea that when the ball reaches its maximum height, that occurs at time t over 2. But there's some other interesting aspects of the ball's motion that we should recognize, and one of them is that the velocity vector v that it's initially given is equal to the velocity vector velocity vector v as it lands, however, with some exceptions. Let's take a look at the components. We should see that the x component of velocity maintains its direction and its magnitude throughout the path that the projectile takes. So you can see that v sub x doesn't change. Vy, on the other hand, is initially positive, but then when it lands, the component of the y component of velocity is the same in magnitude but opposite in direction. You could prove that if you wanted to with some of the equations of motion, but for now we're simply going to use some of these concepts of symmetry to solve the problem and effectively make the math a little bit easier for ourselves. Let's go ahead and start the problem by saying that we know that the final y position could be found by saying that it's going to be opposite in direction the initial y position here. So this is an important idea that I basically grabbed from the symmetry here. Now I can say, I'm going to use the second equation of motion by saying that Vy is equal to Voy plus acceleration times time. And I'm going to solve for t. Rearranging that equation, I get Vy, or I could specify V final y minus V initial y divided by my acceleration is going to be equal to my time. I'm looking for the time now, so I can go ahead and plug in what is v final y. Well, I need to resolve this vector into its x and y components. My initial y is going to be positive 18 meters per second times the sine of the angle, so my v final y is going to be negative 18 times the sine of the angle 35 degrees. And from that, I'm going to subtract my v initial y direction, which is going to be 18 times the sine of 35. And I'm going to divide this whole thing by negative 9.8 meters per second squared. I forgot my units up here for these 18s. Those are, of course, meters per second. Here and here should both be meters per second. Okay, let's go ahead and move this. Now, now that we've done that, we can go ahead and finish this problem. In the last portion of the problem, we'll go ahead and plug some numbers in. Of course, we know that that's all equal to t, and when we run that through our trusty calculators, we're going to get about 2.11 seconds is equal to time. We've dealt with significance, and we've boxed in our answer.